Ethan Reeves, the science guy.
Have you ever wondered how we actually know the Big Bang really happened? Well, got the answer for you. It's all around us after all. Well, space is pitch black, right? So we would expect to find nothing if we were to point an analog satellite dish at the sky, right? So if you point your dish at anywhere in the sky, you'll get the same static over there, over here, or anywhere in general. You'll get the same underlying microwave band static.
This was first discovered by Bell Telephone Laboratories by these two researchers pictured here, who discovered this phenomenon by accident when they were creating a radio receiver. As one of the first receivers to be built, they were using space as something equivalent to a control point for data, expecting to get nothing. So, you can imagine their surprise when they heard something like this. So, now you would think that all this static would need to come from a source that's present all over the sky, but scientists don't know anything, or at least anywhere on Earth, that could possibly do this. So, came up with an idea. Cosmic microwave background radiation, the leftovers of the Big Bang. To see what that truly is, we need to go back just a few years, just a short little 13.8 billion. While the Big Bang happened 13.8 billion years ago, CMB really only dates back to 400,000 years following the Big Bang. And in the early stages of the universe, when it was just 1/100th million the size it is today, its temperature, some would say, would be pretty extreme at 273 million degrees above absolute zero. Any atoms that were present at this time were quickly broken apart into, well, protons, electrons. And the radiation from the CMB and photons, particles representing quantums of light or other radiation, was scattered off the electrons when the atoms split. So these photons wandered through the early universe just as optical light wanders through a dense fog. This process of multiple scattering is what we call thermal or blackbody radiation. About 380,000 years after the Big Bang, the universe was cool enough that hydrogen could now form. Because the CMB photons are barely affected by hitting hydrogen, they continue to travel in straight lines in every direction from the initial bang. Cosmologists refer to a surface of last scattering when the CMB photons last hit matter. After that, the universe was just too big. So when we map the CMB, you're looking back in time to 380,000 years after the Big Bang, just after the universe was opaque to radiation. Early beliefs on trying to discover CMB were that it must be very hot and full of radiation, but as the universe expanded, this radiation cooled down and turned into radio waves, which is why we were able to get an audio clip of what I played for you earlier. So now you might wonder, why do we even care about cosmic background radiation? Whoa, hey, camera back up. Hey, whoa. As I was saying, why do you even care about cosmic microwave background? Well, it's because it helps us learn how the early universe was formed, and it basically gives us the background for everything. From this baby picture of the universe taken from NASA's Cosmic Background Explorer mission, we got confirmation of the Big Bang Theory, and by studying these fluctuations, we can learn about the origin of galaxies and large-scale structures of galaxies, and we can measure the basic parameters of the Big Bang. More studies done by the European Space Agency's Planck telescope also seem to point to the fact that dark matter and dark energy, the mysterious forces that are likely behind the acceleration of the universe, do seem to exist.